We were looking at impact of changes in government spending in the goods market model, where we saw that when we change government spending in the goods market model, as a result of that, over here, as a result of that, we saw that the change in G results in a so basically when G changes, change in equilibrium output, like we saw over here, is greater than the change in G. And we discussed the mechanism of the multiplier effect. Then we looked at a graphical representation of the multiplier effect, according to which when you change government spending, you have a larger effect on equilibrium output. So like we said, we saw that as a result of change in G, change in equilibrium Y is greater than the initial change in G. We discussed the mechanism of the multiplier effect and the graphical representation as well of the multiplier effect. But how do we now mathematically find exactly how much equilibrium output changes? So we know through the multiplier that when you change G, say by delta G, output changes, equilibrium output changes more than delta G. But how much does output exactly change? To find that out, we will mathematically find what we call the government expenditure multiplier, which tells us how much equilibrium output changes due to 1 unit change in G. Now, there are two equivalent ways in which we can derive the government expenditure multiplier in our goods market model. The first approach is to use calculus. So when you want to use this approach, in this approach, we start by solving for our equilibrium output, which we looked at how we solve by just putting, like if we go back a little. So to solve for equilibrium output, let's just go back a little. So yeah, okay, over here. So how do we solve for equilibrium output? We just said y is equal to z, where we find z as c plus I plus g plus nx, and from here we just solve for equilibrium output like we did over here, right? So this is page number 27. So we solve for equilibrium output. So first you solve for equilibrium output, and from the solution of the equilibrium output, we can then derive our multipliers using partial derivatives. In this case, we want to derive the government expenditure multiplier. Now, in a standard goods market model, we found equilibrium output as this. If we just go back quickly, right? So we mathematically found it by setting y is equal to z. We found with z is in the standard goods market model under the assumptions that t is exogenous t given, I is exogenous t given, so is g, and x are 0. It's a closed economy, and we have a linear consumption function. Under all these assumptions, by setting y is equal to z, we found our equilibrium output. So in our standard goods market model, we found our equilibrium output as follows. Now, so you first solve for the equilibrium value of output, and then from its solution, you can derive multipliers using partial derivatives. To get the government spending multiplier, you take the partial derivative of your of the above expression, I solution of equilibrium output with regards to G. So in this case, we take the partial derivative with respect to G bar. So the government spending multiplier is just the partial derivative of I star with respect to G bar, which in this case is 1 by 1 minus C1. So this is one way you can derive your government expenditure multiplier in your goods market model by using calculus. You first solve for equilibrium value Y, which in our standard goods market model under its particular assumptions, investment, government spending, taxes are exogenously given, and it exports as 0. This is the solution. Then if you want the government spending multiplier, you just take the partial derivative of Y star with respect to G bar, which is 1 by 1 minus C1. Now over here, see, we can show that this fraction is greater than 1 by comparing its numerator and denominator. Right? So whenever you want to see whether a fraction is greater than 1, less than 1, or equal to 1, you just compare its numerator and denominator. In this case, C1 being MPC, we know is between 0 and 1, which means that 1 minus C1, which is denominator of a fraction, is less than 1, because from 1, you're subtracting a number smaller, because from 1, you're subtracting a number between 0 and 1, so that's going to result in a number that is obviously less than 1. So since C1 is between 0 and 1, 1 minus C1 denominator of our fraction is less than 1 numerator of our fraction. Right? And if the denominator of the fraction is smaller than the numerator of a fraction, the fraction is greater than 1, right? So if you want to see whether a fraction is greater than 1, less than 1, or equal to 1, you can just compare its numerator and denominator, right? If numerator is greater than denominator, as is over here, the fraction is greater than 1. If numerator is less than denominator, then fraction is less than 1. So what was shown over here is if government spending changes by 1 unit, then equilibrium output changes by 1 by 1 minus C1, which is greater than 1 unit, just as we saw earlier, that the change in equilibrium y is greater than the initial change in g. Because remember, the government spending multiplier is telling us how much equilibrium output changes due to 1 unit change in g. And we can see that when you change g by 1 unit, equilibrium output changes by 1 by 1 minus c1, which is greater than 1. So change in equilibrium y is greater than the initial change in g due to the multiplier, just as we saw. So this is one way in which we can derive a multiplier using calculus, where you start with your solution of equilibrium output and then take partial derivatives. Another way is to use geometric series. More on this later.